Section 11.2 deals with carbohydrate stereochemistry. And if you remember, we talked about stereochemistry back in chapter 8 as being the arrangement of atoms in space. So we might look at two molecules that have the same connectivity, but the arrangement of their atoms in three dimensions or in space is different. And so those would be stereoisomers of each other. Now, in order to get into the details of stereochemistry of carbohydrates, we have to be able to represent stereoisomers. And so we use wedges and dashes to help communicate exactly where bonds are located in the three-dimensional space of a carbon that is tetrahedral. And so we use wedges. So we use a wedge bond to indicate that a bond is coming out of the plane of the page. And you can see that this is a wedge here that we have to this bromine. Okay, so that bromine, that wedge, meaning this dark black part here, means it's coming out towards you. If we use a dash, it means the opposite. So you can see the dash going to the fluorine means the fluorine is going back behind the plane or the screen or the page, whatever. And then these two bonds, the last two bonds, meaning this bond to the chlorine and the bond to the hydrogen. Okay, not my best work. Let me fix that. The bond to the hydrogen. Okay, those bonds are in the plane of the page. And so we just represent them with regular weight lines. Now, moving forward in this chapter, it might be handy to have a handheld model kit. You don't need to have one to complete the chapter at all, but it can be handy to help you understand some of the concepts we're going to look at in this chapter. So again, the dash means the bond is going into the page, like the bond to the fluorine that's shown here, highlighted in yellow, and the wedge means it's coming out towards you. All right. So you might have heard this word chirality or chiral sneak out of my mouth. And a chiral carbon is a carbon atom that has four different groups attached. Notice it says four different groups attached, okay? It doesn't have to be four different atoms, it just has to be four different groups. And if you take a look at this molecule right here, okay, meaning this one here, this is bromochlorofluoromethane. You can see that the carbon in the middle, okay, so the carbon is here, it's attached to four different groups. Okay, technically it's four different atoms in this case, but it's attached to a bromine, a chlorine, a fluorine, and a hydrogen, four bonds to four different groups, and therefore this is a chiral carbon. And sometimes to denote a chiral carbon, we'll put a little star by it like this. So I'm just going to put a star by that carbon to prove or to denote that it is chiral. Now, it says here chiral is a descriptive term for compounds or objects that cannot be superimposed on their mirror image. So if you think about a glove, okay, if you think about a left-handed glove, Mr. Dion is not a very good artiste, but if I draw a left-handed glove, oh, good gravy. And a right-handed glove. Anyhow, that's a terrible drawing. But the idea is that you can't superimpose one on the other, right? Their thumbs are going to be on opposite sides. And so that is why a glove would be a chiral object, right? Your hands are chiral objects. If you hold your hands up in front of you and you put one on top of the other, even though they're mirror images of each other, they don't overlap, right? On one hand, one thumb is going to be pointing in one direction, and on the other hand, the thumb is going to be pointing in the opposite direction. However, objects like a sphere or a cube or chloromethane, which is shown here, have an internal plane of symmetry. And so those are not chiral objects, and so we call them achiral. So we have chiral objects, which cannot be superimposed upon their mirror image, like a glove or your hand or a shoe. However, we have achiral objects that can be superimposed on their mirror image. So if we look at this molecule here, bromochloromethane, meaning this guy, let me use my eraser here, meaning this molecule here, the reason they have that mirror, this is supposed to be a mirror here, is because there is an internal plane of symmetry. All right, and you can also see that this carbon is not attached to four different groups. It's attached to two hydrogens, which are identical, and therefore, by definition, it is not a chiral carbon. Example 11.1 asks us which of the following compounds contains a chiral carbon. Well, if you look at A, you can see that a CH3 group cannot be chiral, right? Because the carbon is attached to 3 hydrogens that are all identical, so that's not chiral. And the carbon that's in the middle here, if you will, okay, meaning this carbon is not chiral. Why is it not chiral? Because it's attached to a hydrogen, it's attached to an oxygen, it's attached to a methyl group, but it's also attached to a methyl group over here. So since that carbon in blue is attached to 2 methyl groups, 2 groups that are identical, it is not chiral, okay? So in this molecule, okay, no chiral carbons. All right, in the next molecule, which is 2-butanol, you can see that the CH2s, like the CH3s, also cannot be chiral because the carbon is attached to 2 hydrogens. So immediately we can alleviate or ignore these 3 here because neither of the or none of these 3 can be chiral, right? A CH3, a methyl group, is attached to 3 groups that are identical. A methylene or a CH2 is attached to 2 groups that are identical. But what about the carbon that's attached to the oxygen? Well, it turns out that is actually a chiral carbon. And so I'm going to put a little red star by this one here because this is chiral. Now, if you don't believe me, this carbon, and I'll circle it in red, is attached to 4 different groups. Remember, I said 4 different groups, not 4 different atoms. It's attached to a hydrogen. That's one group. It's attached to a hydroxyl. That's a second group. It's attached to a methyl. That's a third group, and it's also attached to an ethyl group. So those are 4 different groups, and therefore the carbon in the red circle is a chiral carbon. So we have 1 chiral carbon in that molecule. In the last example, CH3s, CH2s are never chiral, and the carbon that's in the center is not attached to 4 groups, it's only attached to 3, right? It's attached to the methyl, it's attached to the ethyl, and it's attached to the oxygen. And so there are no chiral carbons in that last molecule either. And so remember this moving forward, that whenever you have a CH3, a methyl, it can never be chiral. And when you have a CH2, a methylene, it can never be chiral as well. So we'll put here CH3 and CH2, never chiral. All right, if you're the kind of student who prints out the slides, I want to point out to you that there is a mistake in this slide. Okay, these are the publisher slides, and there's a mistake on here, and I'll show you where it is. But we're going to talk about enantiomers on this slide. And enantiomers are stereoisomers that are non-superimposable mirror images, okay? So a good example of enantiomers would be your hands, okay? Because your hands are mirror images of each other, but they are not superimposable, right? Your left hand won't fit on top of your right hand perfectly. And so if we look at these 2 molecules here, okay, you can see that they have the same connectivity. Both carbons, and the carbon isn't shown in a bond line structure, but both of these carbons are attached to 4 atoms that are the same 4 atoms, a chlorine, a bromine, a fluorine, and a hydrogen. And you can see that they are mirror images of each other. However, these are non-superimposable mirror images. And here's where the mistake is. What they're trying to show you is if you were to take this molecule here, and if you rotated it 180 degrees, what you would end up with would be this. So this is where the mistake is. This should be the fluorine should be here, and the bromine should be here. That's the mistake. And so you can see that the chlorines align and the hydrogens align, but the bromine and the fluorines do not align, right? You can clearly see that the fluorine and the bromine here, right? Those don't overlap. And so these are mirror images of each other, as you can see in the blue box, but they're not superimposable. You can also see that with this ball and stick diagram. You can see that these 2 molecules of bromochlorofluoromethane are mirror images of each other. However, if you take this one, and this one, there's no mistake, but if you take this and you rotate it 180 degrees, so you flip it over, it's going to look like this. And you can see that these 2 molecules are not superimposable, right? The chlorines and the hydrogens will overlap, but the fluorines and the bromines will not. You can see the fluorine is going into the back, and so is the bromine. So you can see these are not identical. So again, Enantiomers are mirror images that are not superimposable. And if you're saying, "Oh, Mr. Dion, you're just not rotating it the right way, or you're not manipulating it the right way, Mr. Dion," well, I can tell you that I am right. And what you could do if you don't believe it or if you can't see it would be to get a pair or a set of handheld models, build these two molecules, and you'll see there's nothing you can do. You can flip them around and jumble them around any way you want, but they're never going to superimpose upon each other, even though they're connected to four atoms that are the same. So again, by definition, they're stereoisomers, but more precisely, they are enantiomers. Stereoisomers that are non-superimposable mirror images. Now, some molecules have multiple chiral centers. For example, if you take a molecule like cholesterol, I think it has something maybe 8 stereocenters, maybe more. So, organic molecules, especially carbohydrates, that's why this is coming up in this chapter, may contain more than one chiral carbon. If you remember erythrose, we saw it in a previous video, it has two chiral carbons, right? So this is a chiral carbon and this is a chiral carbon. And you could practice yourself, convince yourself that this carbon, this one here, is attached to four different groups. And you could practice to convince yourself that this one is attached to four different groups. Remember, it's four different groups, not four different atoms. So when a molecule contains more than one chiral carbon, the possibility exists for two arrangements of attached groups at each chiral carbon, right? We can reverse the stereochemistry at any chiral carbon, and thus nearly all molecules with two chiral carbon atoms exist as two pair of enantiomers or for a total of four stereoisomers. Now, if you're wondering, where am I going to get that number from, the four total stereoisomers? Well, the general formula for the number of stereoisomers is going to be the maximum number of possible stereoisomers is 2 to the power of n, where n is the number of chiral carbons. And so if erythrose has a total of 2 chiral carbons, we take 2 to the power of 2, which is equal to 4. So that means that erythrose has 4 stereoisomers. Okay, the carbohydrate deoxyribose, shown here, right here, can react to form a ring, which is the way it is found in DNA. Serine is an amino acid. A building block of proteins. Draw enantiomers of them in dash and wedge notation. So if we're going to use dashes and wedges, we're going to use skeletal structures or bond line structures. And so what I'll do for deoxyribose is I'm going to do like this. So 1, 2, 3, 4, 5. And so if I number these as carbons 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, like that. You can see on carbon number 1, we have our aldehyde. I'll abbreviate that CHO. On carbon 2, we have a CH2. On carbon 3 is a chiral carbon, so I'm going to put um, dash and wedge notation. So I'll just draw, this is coming up like this as a wedge. And then for the other one, for carbon number 4, I'll draw hydroxyl. It's coming out like this. And then the last one, there is no chiral carbon here, so I'll just put OH like that. So now if we want to draw the enantiomer, we can draw the mirror image. Now, if you look at the way they solve this in the textbook, it's a little bit different. Now, the way that they did it, and this is the solution that you have in the slides. Normally, I don't refer to these, but it says here in their answer is that they just arbitrarily chose this as a wedge and this is a dash. I chose to draw two wedges, which is neither here nor there. They just want you to draw the enantiomer. So you can draw the enantiomer the way they did it here, where you just draw the mirror images. The mirror image, excuse me, the way they have here, and there's nothing wrong with this. This is 100% correct. But if you go back to my strategy here, there's another way you can draw the enantiomer that might be easier for you. And that is all you have to do is take anything that's a dash and change it to a wedge, and anything that's a wedge and you flip it over to a dash. And that would be considered an enantiomer. So what I can do is I can just use the magic of the iPad and I can just copy and paste this molecule here. Okay, so I just copied and pasted it. And since I drew two wedges, all I'm going to do is delete those and I'll change them into dashes. So again, you just have to flip every stereocenter, and now I have a pair of enantiomers. Okay. Now for the serine, in the serine, there's only one chiral carbon in there, and that's this one here. It's attached to 4 different groups. And so again, I'm going to use a bond line structure for this. But we have 1, 2, 3. So we have our COOH. Then we have our OH over here. And then for the bond to our nitrogen, I'm just going to choose a wedge like this, and you could have used a dash. It's totally fine. So then to draw the enantiomer, you've got one of two possibilities, okay? One would be just to reproduce the same thing. So I'm going to copy this and just paste it over here. Okay, and I'll change the color. So, and what we're going to do is we're just going to flip the wedge to a dash, and that would be a pair of enantiomers. Now, you can also try and draw the mirror images. I just keep saying that, mirror images. The mirror image. It's a little trickier, but maybe students like that more. I don't know. Okay. So this is the mirror image. And so there's nothing wrong with drawing it, but I just think it's easier to just flip every wedge to a dash and every dash to a wedge.